In this video, we will discuss inscribed and circumscribed regular polygons and circles. A regular polygon is a polygon where all sides are the same length and all angles are the same measure. To find the number of degrees in each angle of a regular polygon, first subtract 2 from the number of sides. Then multiply the result from step 1 by 180 degrees. And finally, divide the result from step 2 by the number of sides. The degrees per angle of a regular polygon is equal to 180 degrees times the number of sides minus 2 divided by the number of sides. There should be parentheses around the number of sides minus 2. That's what you do first. You subtract 2 first, and then you multiply by 180. Sorry about that. Find the number of degrees in each angle of these regular polygons: triangle, square, pentagon, hexagon, octagon. A triangle has 3 sides. The number of degrees in each angle of a regular or equilateral triangle is 180 degrees times 3 minus 2 over 3, which is 180 degrees times 1 over 3, or 60 degrees. A square is a regular quadrilateral. The number of degrees in each angle of a square is 180 degrees times 4 minus 2 over 4, which is 180 degrees times 2 over 4, which equals 360 degrees over 4, which is 90 degrees. A pentagon has 5 sides. The number of degrees in each angle of a regular pentagon is 180 degrees times 5 minus 2 over 5, which is 180 degrees times 3 over 5, or 540 degrees over 5, which is 108 degrees. A hexagon has 6 sides. The number of degrees in each angle of a regular hexagon is 180 degrees times 6 minus 2 over 6, which comes out to 120 degrees. And an octagon has 8 sides. The number of degrees in each angle of a regular octagon is 135 degrees. A regular polygon can be divided into as many congruent triangles as there are sides of the polygon. To form congruent triangles in a regular polygon, first draw line segments from the center of the regular polygon to each vertex. The congruent triangles are then formed. To find the area of a regular polygon, find the area of one of the congruent triangles formed by connecting each vertex with the center of the polygon. Then multiply the result from step 1 by the number of congruent triangles. So for example, find the floor area of a recreational building at a park if it forms a regular hexagon and each side is 20 feet long. The perpendicular distance from one side to the center of the building is 17.3 feet. So we divide the regular hexagon into congruent triangles by connecting the center of the hexagon with each vertex of the hexagon, then calculate the area of one triangle. That is, the area of one triangle is 1/2 times the base times the height, which is 1/2 times 20 times 17.3, or 173 square feet. The area of the hexagon is thus 6 times 173 square feet, which is 1,038 square feet. A polygon is inscribed in a circle when it is inside the circle and all its vertices or corners are on the circle. The circle is circumscribed about the polygon. A polygon is circumscribed about a circle when it is outside the circle and all its sides are tangent to, touching at exactly one point, the circumference of the circle. Specifically, the circle touches the midpoint of each side of the polygon. The circle is inscribed in the polygon. If a square is inscribed in a circle, the radius of the circle is 1/2 the diagonal of the square. The diameter of the circle is equal to the diagonal of the square. The side of the square is equal to the diameter of the circle divided by the square root of 2. And the diameter of the circle is equal to the square root of 2 times the length of the side of the square. If a square is circumscribed about a circle, the side of the square is equal to the diameter of the circle. The radius of the circle is 1/2 times the side of the square, and the diagonal of the square is equal to the square root of 2 times the diameter of the circle, which is 2 times the square root of 2 times the radius of the circle. To mill a square bolt head 1.5 inches across flats, round stock of what diameter is needed. Answer to the nearest hundredth. The distance across corners is the diameter of the circle, and the diagonal of the square. The distance across flats is the side of a square inserted in a circle. So the diameter is equal to the square root of 2 times the side of the square, which is equal to the square root of 2 times 1.5, or about 2.12 inches. The diameter of the round stock is 2.12 inches. Find the diagonal of an inscribed square if the area of the circle is 22 square inches, round to hundredths. The area of the circle is equal to pi r squared, so 22 equals pi r squared, which means 22 over pi is r squared. So r is the square root of pi over 22, which is about 2.646283714. The diagonal of the square is equal to the diameter of the circle, or twice the radius. Since the radius is 2.646283714, the diagonal of the square is 2 times that, which is about 5.29 inches. What is the maximum depth of cut required to mill a circle on the end of a square piece of stock with a side measuring 4 centimeters? Answer to hundredths. The side of the square is 4 centimeters, so the diameter of the circle is 4 centimeters, and the radius is 2 centimeters. If the radius is drawn perpendicular to the top side, a right triangle is formed as indicated in the diagram. Let D equal the depth of milling, which equals the hypotenuse of the shaded triangle minus the radius of the circle. Then C squared equals A squared plus B squared, which is 2 squared plus 2 squared, which is 8. So C equals the square root of 8, which is 2.827427125. Since the radius of the circle is 2 centimeters, the depth of milling is D equals 2.827427125 minus 2, or about 0.83 centimeters when rounded. Since equilateral triangles are regular polygons, they can be inscribed in a circle or circumscribed about a circle. The height of the equilateral triangle has a special relationship with the radius of the circle. The height of an equilateral triangle divides the triangle into two 30, 60, 90 triangles. By relating the radius of a circle to the height, we can then determine the length of the side of the equilateral triangle. If an equilateral triangle is inscribed in a circle, the radius of the circle is 2/3 times the height of the triangle. The height of the triangle is 3/2 times the radius of the circle. The side of the triangle is 2 times the height of the triangle divided by the square root of 3. The side of the triangle is 3 times the radius of the circle over the square root of 3. And the radius of circle is the square root of 3 times the length of the side of the triangle divided by 3. The equilateral triangle inscribed about a circle, circumscribed about a circle, the radius of the circle is 1/3 the height of the triangle. The height of the triangle is 3 times the radius of the circle. The side of the triangle is 2 times the height of the triangle over the square root of 3. The side of the triangle is 6 times the radius of the circle divided by the square root of 3. The radius of the circle is the square root of 3 times the radius of the circle divided by 6. Find the dimensions for the inscribed equilateral triangle in the figure below, where CD equals 13 millimeters and AO equals 15 millimeters. The height of triangle ABC is 3/2 times the radius of the circle. The height of the circle of the triangle is AD, and the radius of the circle is AO. So AD equals 3/2 times AO, which is 3/2 times 15, which is 45 divided by 2, or 22.5 millimeters. We want to find BD, which is equal to CD. Since CD is 13 millimeters, and since corresponding sides of congruent triangles are the same length, BD is also 13 millimeters. We want to find BC, which is equal to BD plus CD. BD and CD are both 13 millimeters, so BC equals 13 plus 13, which is 26 millimeters. We want to find angle CAD. Since triangle CAD is half of an equilateral triangle, it is a 30, 60, 90 degree triangle. Since CD is opposite angle CAD and is the shortest side, angle CAD is 30 degrees. We want to find angle ACD. We already know that angle CAD is a 30 degree a 30, 60, 90 triangle, and angle ACD is opposite the height. So angle ACD is 60 degrees. We want to find the area of triangle ABC. We know its height, h equals 22.5 millimeters, and its base, b, is 26 millimeters. So its area is a equals 1/2 bh, which is equal to 1/2 times 22.5 times 26, which is 22.5 times 13, or 292.5 square millimeters. One end of a shaft 35 millimeters in diameter is milled as shown in the image below. Find the radius of the smaller circle. BC is the radius of the large circle, so its length is half the diameter. Therefore, BC is 1/2 times 35, or 17.5 millimeters. The height of the triangle AC is 3/2 the radius of the circle, so its length is 3/2 times 17.5, or 26.75 millimeters. Finally, the radius of the smaller circle AB is 1/3 AC, since the circle with center B is inscribed in the triangle. AB equals 1/3 times 26.25, which is 8.75 millimeters. A regular hexagon is a figure with 6 equal sides and 6 equal angles of 120 degrees each. Three diagonals joining pairs of opposite vertices divide the hexagon into 6 congruent equilateral triangles. The hexagon is inscribed in a circle. The diameter of the circle is equal to the diagonal of the hexagon. The radius of the circle is equal to the side of the hexagon. The diagonal of the hexagon is 2 times the side of the hexagon, and the distance between parallel sides of the hexagon is the square root of 3 times the side of the hexagon. If a hexagon is circumscribed around a circle, then the distance between parallel sides of the hexagon is equal to the diameter of the circle. The diagonal of the hexagon is equal to 2 times the side of the hexagon. The radius of the circle is the square root of 3 times the side of the hexagon divided by 2, and the radius of the circle is the height of one triangle formed by the 3 diagonals. If a regular hexagon is cut from a circle with radius of 6.45 inches, how much of the circle is not used? Round to hundredths. To solve, we find the area of the circle and the area of the hexagon and subtract to find the difference. The area of the circle is pi r squared, which is pi times 6.45 squared, or pi times 41.6025, which is equal to the 130.6981084 inches squared. The area of the hexagon is 6 times 1/2 bh, which is 6 times 1/2 times 6.45 times the square root of 3 times 6.45 over 2, which is 6 times 1/2 times 6.45 times 5.585863854, which is equal to 108.0864656 square inches. The waste is the difference between the area of the circle and the area of the hexagon, which is 130.6981084 minus 108.0864656, or 22.61 square inches when rounded.